Good day, everyone. My name is Rebecca Lilly for the International Association for Energy Economics. It gives me great pleasure to welcome you to today's webinar entitled Electric Vehicles Economics, Managing the Adaptation of Energy and Mobility Systems. We're grateful to our moderator, Yannick Perez, and our distinguished panelists for today's timely discussion. First, a little bit about the International Association for Energy Economics. We are the largest association specializing in the field of energy economics and provide a forum for the exchange of ideas, experience, and issues among professionals interested in the field. The organization produces 2 professional journals, a newsletter, and holds conferences and virtual presentations, along with a host of other products and services that you can find at our website at www.iaee.org. If you're not already a member of the association, we welcome you to join. A few housekeeping matters in regard to today's webinar before I hand things over to our moderator. First, this webinar is being recorded for those that cannot participate in today's live event. If you have questions for our panelists, please click the Q&A button at the bottom of the Zoom window and type your question. We've allocated time to read and answer your questions. And now I would like to introduce you to our moderator, Yannick Perez, professor in economics and energy and mobility at the University of Paris-Saclay. Yannick, over to you.
Thank you very much, Rebecca. Welcome everyone to this seminar today. We will have 4 presentations. The first one will be a duet between Willett, Kempton and McGee. Then we will have Remi, then Willett Arevalo, and I will conclude and replace Marc-Olivier Mettet for the last presentation. It would have been better than Marc-Olivier could make it, but he's stuck somewhere in a strange airport in the Northern Europe, so he cannot make it today. So he sent us his apologies and slides, so at least we will have his views on the problem of infrastructure charging requirement. Without any further introduction, I will pass the duty to start to Rodney and Willett for their presentation on the standards for electric vehicle and energy systems integration. Please, guys, the floor is yours.
Thank
you very much. I'm Willett Kempton.
I'm Rodney McGee.
And I'm going to start out, and then Rodney's going to cover the other half. We are going to talk about new standards for communications, which enables a lot of EV economics. We're not going to have economic data in this presentation. So the standards are Society for Automotive Engineers J3068 and J3072. This gives our affiliations, but we're both part of a research and development group at the University of Delaware. Just to give a sense of where we're coming from, we have competencies in EV engineering, electrical standards, both in Europe and in the United States, and also policy requirements. So how do we get high value V2G and grid services? So that requires all of these pieces, the technical systems, standards for those systems, and policies that enable achieving grid services and which makes the grid more reliable and more steady, and then revenue for those. We also have to, in the end, deal with tariffs and requirements at the RTO level in the US, TSO level in Europe, and also the distribution companies. So those are the areas that we cover in our group of about roughly 10 people. So we take on projects to show cost-effective engineering, if we can, market entry as well. So there's 2 different tests. One is, does the system work, and the other is, are you allowed to enter a market and make money at it. We are trying to apply new standards and new rules. So we're always getting the arrows in our back from being out in front. Rodney in particular is chair of a standard committee that we'll be talking about. So we're very involved with this. And we try to engage industrial partners, which gives us realistic feedback and can lead then to more quick commercial deployment if we're already working with a party. So most of you understand the idea of a grid integrated vehicle, but just quickly for those who have not seen it before, you have an electric vehicle which contains storage, and it contains a way of bringing power off the grid and maybe pushing it back onto the grid. So we want to integrate that electric vehicle into the electric system. So that's a grid integrated vehicle, and that can provide benefits to consumers, but also to other ratepayers. It can provide technical benefits to the grid itself. On the EV side, it can bring down the total cost of ownership because you've got a second revenue stream. When the EV is parked, you may be earning money, or you may have some compensatory payment like lower cost charging or free charging in some locations. And from the overall load perspective, it turns an uncontrolled influx of demand into a controlled load. So even if you're just controlling the rate of charging and there's no backfeed, no V to G, you at least have that control of new load. Of course, the grid's changing as we speak. There'll be much more variable generation online every day. There's more. So this also provides a large storage add to the grid, which is going to be very low cost because the storage has been bought for the purpose of transportation, and we know at least privately owned vehicles are only used about 5% of the time. So you've got potentially large storage resource coming online. It's going to be grid connected anyway, and most of the time it's not being used for the purpose it was purchased for. Technology is proven. Some OEMs and some tier one suppliers to the OEMs, when I say OEM in this context, I mean automobile manufacturers. There is production already. There's not really large scale production of the vehicles that are ready to go, but this is already happening. But there's still a lot of barriers that we're dealing with. So interesting institutional issues here. You've got two large, highly developed industries which are very entrenched. They're not used to interacting with each other. That is the electric power industry and the automotive industry. They're regulated by completely different laws, regulated by different agencies. The standards making organizations have very rigid boundaries of what they include and what they don't include. And even the people, the expertise, knowledge, and the terminology have a little overlap. So it's really kind of daunting to connect these two industries. They are, this is also a multidisciplinary problem, trying to make EVs useful to the power grid. Yet the two industries have very traditional ways of looking at things. And so there's a bit of resistance to change, I think, in both of these industries. My apologies to some of my colleagues in each of these industries, but I think you would agree that that's true of many of your colleagues, whether you're in the automotive or the power industry. So the resource that we're talking about, that is batteries and power electronics in EVs, have these two very different use cases. A lot of times they're compatible, but they will sometimes be different. Sometimes by using the power and the battery for grid services, you may not have as much margin of error in your next trip. So we think that that's very manageable, but we have to acknowledge that there will sometimes be a different, differing objectives, and sometimes they will conflict. And of course, there's more use of the battery. So there's an argument you have more rapid wear. Also, we think this is manageable, but again, we acknowledge that there are sometimes differences for these different use cases that we're talking about. But it's a kind of revealing general point that summarizes a number of these, which is that the end of the charging station connector, where you plug into the vehicle, that's a major boundary between these two worlds. And that discontinuity we found is really the major challenge. There are others, but there's the major challenge to development of EVs as grid integrated vehicles. So we're going to address that here. What are the standards and the electrical requirements where you connect the EV to the world of electricity? Two system types, just to sort of quickly look at this, DC and AC charging, and that's referring to the power flow between the charging station and the vehicle. Is it DC or AC? Of course, there's AC on the grid side, and there's DC inside the vehicle where the battery is. So where do you change over from AC to DC? Is it in the vehicle or on the charging station? And that's what's referred to as DC charging versus AC charging, but there's AC and DC in both systems. It's just where the boundary occurs. So the advantages of DC charging is the development work by the OEM. Now, this is if we're going to make grid integrated vehicles. How are we doing it? So the OEM's development work is really minimal. They've already got a DC connection for fast charging in many cases. The extra cost is off board. So from the OEM perspective, great. All that expensive stuff is somebody else's problem. The regulatory path is more traditional. You're looking at the characteristics of this device in the fixed in place, bolted to the building electrical system, rather than worrying about electrical standards in a mobile device, which is global. The grid integrated vehicle use case may conflict with just the idea of filling up and going, but you've got that as one problem and others are sort of solved in that system. Whereas the AC system for grid integrated vehicles, where conversion is occurring in the car, that's really where the cars are going to be most of the time. Okay, so this is more en route charging, DC charging, but the cars are parked and stationary, which is where they're valuable for grid integration. In this case, where it's AC charging. And that's partly because system cost typically is going to be much lower. And it turns out to be more complicated than you might think why the system cost is lower, because you've got conversion in both cases. But this lower cost and where the car is most of the time, those are pretty strong considerations for why we want V2G to work in this case. And also, when you have this kind of system, it allows for other features like vehicle to load, remote vehicle. You're running power tools, you're running some kind of camping equipment, and vehicle to vehicle. You know, if in the AC charging case, it's easier to run a direct charge from one vehicle to another, which we're going to be wanting to do. We're not going to have jerry cans, walking around. We're going to want to be able to plug that remote discharge vehicle into another vehicle that comes along. So this is kind of an overview of AC and DC charging without getting into standards and so forth, but just what are the pros and cons. And also explaining why we put more emphasis on the AC charging side. We want to work in both. We want to have solutions for both. But so there's lots of standards already. As soon as we start saying, well, we need a standard, we immediately get hit by a bunch of fruit and other harder devices, other harder objects. So why is there a need for a standard? There are, of course, several standards for charging. We think it's important to have an integration of an electrical standard and a communications protocol, not just separate out the communications protocol as the thing that's being standardized. And again, long story behind that, but that's our claim here. It has to be worldwide, and we don't have really good worldwide standards. The electric companies are local and automotive companies are global. You know, that's sort of another disjunction, really. But for something that is going to be put on automobiles, it really has to work worldwide. Some manufacturers, of course, are only selling to a region, but many are trying to produce world cars. So that means, you know, you have to work with different electrical requirements in different areas. You have to work with single or three phase. You have to work with, you know, 100 volts in Japan and 600 volts in Canada and everything in between. And then there's a problem here, which is for a worldwide standard. How do you make a roaming inverter that is going to be made for world use? And how do you have that meet local electrical requirements, which are different in different countries? Of course, we're getting more harmonization in the EU, the US, we've got different standards in different states, and so forth. And you want features. So like we kind of now realize we want plug and charge. Of course, that's got to work. You know, you just have to have plug and charge. You want rich V to G capabilities. Maybe that's a Delaware bias or whatever. We think that's very important also. And you want to have access to TSO markets and DSO markets. And we kind of now realize there's not going to be just one standard to rule them all. So we want a standard that can be handed off to other means of communications. So you do direct, hardwired association with serial numbers or something between the account numbers between the vehicle and the charging station. You know who's connected, it's through the wire, you know who's who, then you can hand it off to Wi-Fi, OEM telematics, PLC even, to another physical layer and another standard potentially. That's okay, so that's allowed, but we think it should be allowed in standard. And of course it should be low cost. You know, you don't want a standard that mostly relies on one chipset that, oh, it costs $250 per vehicle, but that's okay. You know, there's lots of hardware protocols that can be done with, you know, $5 or $10 worth of chips that are fairly standard. So, you know, it turns out OEMs care about something that costs $5 versus $250. Who would have thought? And of course, we want highly reliable standards for reasons that we'll go into more so for V2G. We'll come to that. So I'm going to pass the baton to Rodney at this point. I'll turn the slides.
Yeah, so one of the key issues with having a vehicle interconnect to the grid is that traditionally everything that's interconnected to the grid is very much permanently installed. It's been looked at by local inspectors. They put stickers on it. They check file numbers. They fill out paperwork. They sign things. They tag things. They write it down. This serial number is installed at this location. So if you have a vehicle that can drive up to a charging station and you want that vehicle to be able to push power back into the grid, the way we have done interconnections is fundamentally not set up for that. So, but it's not just plugging into some random outlet, it's plugging into a specifically designed charging station. So with this standard that we started working on in 2014, J3072, what we really address is having the charging station be the gatekeeper to the grid. And what that means is the station is actually, you know, in the words of Southern California Edison, they're interconnecting the charging station, even though the vehicles come and plug in. That's because the charging station's permanently installed. The inspectors come and looked at it. It contains the settings that are specific to that grid. So if you had a car that had to drive between California and Nevada, and in Nevada, they required a particular kind of electrical setting that they didn't require in California, the car gets correctly configured when it happens in both locations. That is very novel. This concept, that specific thing I just described is still only described in J3072, international standards by like IEC and ISO standards. They haven't gotten to that point yet, right? They're still looking at V2G as we plug in a car, we tell it to charge and discharge, but it's more complicated than that because the vehicle has to be configured to what Europeans call grid code. that is currently in Europe becoming one unified grid code. Right now, it's each state has their own within the European Union. Each country has their own grid code. And in the United States, we mostly have the same grid code, but it can be configured differently depending on the needs of the region. So that's basically what the standard does. You can see some of the details there. It can check to see if that vehicle's on an approved list. It can just make sure the vehicle's been configured right. And if the vehicle doesn't behave, it can disconnect it, right? So that's the important thing. It gives the people in the power industry something that's UL listed, that's gone through all the typical regulatory tests, and it's the person in between that vehicle that just drove up, right? So that's one of our standards. The next one is a connection standard. So what we just described in the previous one is the car plugs in and gets configured to backfeed onto the grid. Well, how does it actually connect? And so there was a real lack of standardization for vehicles that covered medium and heavy duty in North America. So, any of you know, and just a little bit of technical stuff about the electric grid, that it's a three-phase system. That's what we use worldwide when we generate power. Sometimes we use DC in certain links, but generally speaking, it's a three-phase grid. And so the power gets delivered to large users in three-phase. So we wanted a North American standard that could handle single-phase and three-phase. Also, that allows for higher power levels. So if you have a standard that's meant for passenger cars, and it's sized for the batteries on passenger cars, when we went to these bigger vehicles, or even vehicles with bigger batteries, we wanted to deliver more power. All right, and that makes the vehicle more useful as a storage resource, but also makes the vehicle have more utility by being able to charge it up quicker. Okay. There's a number of features that we wanted to have. It's important that if you imagine charging station operators, they're kind of in the dark ages right now. Like if you were a company and you just bought electric vehicles, and you just plug them into your motor pool where you keep your vehicles, you wouldn't know if a car is charged correctly or not, or if a charging station went offline. And so very simple things like to know vehicle 6 is plugged into charging station 3 and it's full, or vehicle 5 stopped charging at 5 a.m. because of a problem. Like, we want those kind of features because those are what industry needs to actually electrify transportation. If you don't have that, you have a system that in some ways is inferior to what it replaced because they don't have visibility into whether the cars are ready to go, right? So that's an important thing with this standard. Also, we really wanted to focus on low cost, non-proprietary worldwide standards. Some of the other standards are patent encumbered. They're also, there's only one automotive qualified vendor for some of the other standards. So these are major barriers to adoption, especially in Asia, where there's a real aversion to adopting standards which are heavily patent encumbered. Next slide. Okay, so what are some issues today with V2G? Well, I would say that from the technical side, we've talked a little bit about regulatory issues. On the technical side is many of the existing standards and protocols are not reliable enough for V2G. Well, why do I say that? Well, with V2G, you have to be more reliable than simple unidirectional charging. But you might say, why? Well, with unidirectional charging, you charge, you fill up, you shut down, right? You plug in your car, it starts charging, it fills up, it goes off. It fundamentally can only provide a resource while charging. So you can maybe slow charging down a little bit, but once it's full, it's full. When you have a bidirectional power connection, You can put power onto the car and take power off. That means that the vehicle can almost continuously operate whenever it's plugged in. Longer operation means in order for you to not have an error while charging or an event, you have to have more reliability. Also, think about if you're taking power off the vehicle, you have to be very certain you can put it back on. If you have a glitch after you've taken the power off, then the car could theoretically have less power than when the driver plugged it in. 1 or 2 times that happens to a driver, they don't want anything to do with it. They're done. So that's why when we have these sort of advanced functions, they need to be more reliable than the unidirectional case. And today, our unidirectional reliability for DC fast charging for North American and European standards are pretty poor, okay? So this is the so-called CCS system, which is used in North America and Europe. It's not used in China or Japan. It's fairly unreliable. It's probably very few people in the industry will say this, but it's probably the most unreliable fast charging standard in the world. It might also be the most secure, but it is also the most unreliable. And a colleague from Berkeley worked on that 7% of the, 6.4% of the time, there was just a failure to start up, right? I'll, ignore broken connectors and things like that, but that's just everything's correctly functioning, but the system just doesn't initialize. It's like if you plugged in your phone, error, plug it in, unplug it again. And sometimes these events happen after you've plugged in. Okay, so after you've walked away. If you're right there waiting for your car to fill up because you're on the interstate, that's okay. Maybe you charge, plug in again, right? But if you're at home and you've walked away from your car, you don't want to have to be thinking about whether it's charged or not. So reliability is a huge unsolved issue, not widely discussed. Everyone's just deploying. But meanwhile, the Chinese have many more electric buses than are in North America and Europe. And investment is a part of that, but I would also say standards don't allow for industrial use for these standards that were originally developed for the consumer industry. Next slide. So I mentioned this earlier. If you talk to anyone in one of these industries, they'll tell you it's okay. 15118-20 has solved all problems. Just use this standard. One of the issues with that is it doesn't handle the grid code compliance issue I talked about, which makes it not usable for AC-V2G. It also, the IEC hasn't started working on the equivalent charging station safety requirements yet. So that's going to be many years before that can be published. The standard I mentioned before, 3072, does solve that problem, and it isn't tied to specific implementations. So you can use the concept of 3072 for other communication standards. I think that's probably all I want to say about that. Let's go to the next slide. So where we are, well, most of these standards have been published. 3072 is in its second draft. 3068, second draft. So actually the second version has even been published. And they're probably working on the third version is in a draft. 3068 we've have published since 2018. There's a new version to be published this year. We're working on new standards for association and vehicle to grid. We at the university publish open source hardware and software implementations. OEMs are working with us on that, and charging stations are commercially available using some of these standards. Also, I'll just mention it, the Hyundai Ioniq vehicle, which is launching both, it's in many markets, European, American, and even I think in Australia and New Zealand, they're selling these vehicles. The vehicle that's coming out this year is going to be V2G capable hardware, V2X actually, so it can do those vehicle to load, vehicle to home kind of functions too. So these functions are definitely coming to vehicles, and if the standards are there, we'll be able to use them to help the adoption of renewables. But if the standards kind of aren't, there's just going to be more barriers to the adoption of the technology.
Sorry to interrupt. 3 minutes to conclude. Oh, okay. You did it in 3 seconds. You're great. Thank you very much for your presentation. Very exciting and very interesting. We have a question in the Q&A zone. For two-wheels drive scooters, motors play a very important role in developing countries where millions of units are being sold. This will require a lot of work on adaptation of energy and mobility systems. Do you have ideas and or comments on this issue regarding, I guess, standards and?
Yeah, the approach that we came up with, the 3068, I talked about it a lot with medium and heavy duty big trucks and buses, but it's a fundamentally very cheap. The communications requirements are, less than $1, but the functions are very high. So I think it would actually work very well for these small vehicles. In fact, in some ways it might be more optimal. There was some work in the IEC to do a electric vehicle charging standard focused on small vehicles. I don't think that's gone anywhere specific, but I think the infrastructure we use for passenger cars, if you choose the right standards, it can be very low cost and easily deployed in emerging markets.
Okay, there is a second question regarding the adoption of two-wheelers and the problem of having the development of charging stations, local workshops to repair them, etc., which is more a question about the emergence of, let's say, an environment which will help the development of the technologies. But I don't know if it's a question or a remark, maybe both of them.
Well, that's not something we've really looked at in detail, that overall infrastructure for charging two-wheelers, but yeah.
You have a little bit. So Willett has looked into charging infrastructure in dense urban areas, and some of your ideas related to those might go pretty well. I think the primary driver there is making sure that safe electric vehicle charging infrastructure, the costs can go down low for those. And I think given the massive production for electric vehicle chargers, the cost has come down a lot. And so I think these very simple chargers that were required for these vehicles can be, a lot of the development cost is being bore by the sort of larger vehicles, and then that technology can trickle down into the smaller vehicles at a lower cost. Certainly the cost of a charging station has decreased a lot over the last couple of years.
Thank you. Is there a last questions regarding this first discussion and presentation? No, so maybe people will raise more questions on the Q&A later on. So we are going to move to the second presentation by Remi. So your mic is off, now it's on.
Let me share my screen.
Yes, please.
And there we go. Do you see my screen properly?
Yes, perfect.
Okay, so hello everybody. My name is Remi and I'm a third-year PhD student at Central Supélec, and working also with the French transmission system operator RTE. And today I will talk about the integration of electric vehicles into transmission grids in a prospective time horizon and with a focus on Europe. So the outline of my presentation would be first introducing, then presenting the methodology, a case study, and then concluding. So to begin with, as an introduction, as a lot of us know, transport is one of the main CO2 emission sectors. So we expect to have a lot of electric vehicles in the coming years in several countries. For instance, in Europe, we have planned the sales of we have planned the ban of sales of thermal vehicles in the coming years in most of the countries, and as a result, we can expect up to 75% EV sales by 2030. So that's the scope of study of today's presentation. We see several areas of interaction between electric mobility and power systems when it comes to EV charging flexibility. We have first, when we look at decades, how do we invest into generation and network? How do we take into consideration the demand flexibility into those studies? Secondly, when we look at yearly or monthly studies, we have two questions, which are how to optimize our generation load adequacy in order to minimize cost and emissions. Thirdly, we have also on this time range the flows on the transport and distribution grid, so in order to minimize the congestions on the grid. And lastly, when we look at the day ahead on intraday markets, we have a potential on those markets. And lastly, there's a question also of grid frequency regulation when in a matter of real-time connection. So in today's presentation, I can not obviously focus on all those aspects. So I'll focus on the second one, which is the optimal dispatch of electricity. So in this area, there is some gaps in the literature, especially to study the large diffusion of EVs at national data, at a national scale, and also to evaluate how EVs will influence the electricity prices and generation. So my research questions today would be, to what extent and under which conditions can the electricity system accommodate a large number of EVs? And also, what cost reduction can we expect from demand-side flexibility on the electricity dispatch? So in order to study these questions, my methodology will be split into two consecutive parts. So first, on the right-hand side, on the left-hand side of this graph, we will try to model how demand can we expect from electric vehicles. And secondly, some electrical system modeling to evaluate which generation means are used and what are the emissions and costs of the system. So when we focus a bit on the first part of our methodology, to begin with, we have to study travel surveys in order to generate input data for the trips that we will simulate. So for our case study, we used the most recent French travel surveys, which shows that there's kind of differences between several parameters for the trips, which is we have to distinguish between short trips, so close to home, which the user would mainly charge back at home, and long distance trips, where the EV driver would need to connect in the middle of the trip. We also have some differences between rural and urban areas on this data, with rural drivers who drive longer distances and get to home a bit earlier. And we also have some difference between the different social personal categories and the day of travel with longer distances on the working days. So when we studied this travel surveys, it provides us the input data in order to compute the demand of electric vehicles. So in order to do so, we use an algorithm which belongs to the category of the statistical usage of travel data models. which relies on generating a large number of vehicles, and then we have a Monte Carlo analysis to generate a statistical representative data for an average EV. And in the end of this algorithm, we provide several outputs. So the main one is the demand curve of vehicles when they are not, when their load is not controlled, so uncontrolled scenario, but also the amount of vehicles that are connected to a grid, and also the total capacity connected to a grid, which then enables us to study the demand flexibility in the last step of our methodology, which is integrating this data into a power system model. So for a case study, we selected the model called Antares Simulator with one node per European country, or more precisely European price zones, as some countries are split between multiple price zones. And when we take the basic European system data, we had two nodes for electric vehicles. So we had one with uncontrolled EVs, and another node in order to model the smart charging of these EVs. And for this study, we study only smart charging of vehicles inside France, but inside a framework of the European system. And what the model provides us is the adequacy between generation and load, as illustrated on the right-hand side of this slide. And we see that there's in dark green the EV demand, which is in this scenario smartly charged, and there is a kind of adequacy between the optimal EV demand times and the generation in the system. So when we look at the results of our case study, so firstly we selected some hypotheses for EV development, which are in line with kind of the most ambitious EV development scenarios. So we selected the 2040 time horizon, and we estimate that at this time horizon, there'll be up to 24 million EVs in France, which is around 2/3 of all individual vehicles. And we also selected the hypothesis of around 78 kilowatt-hours average battery capacity for battery electric vehicles. And secondly, regarding the prospective electricity generation, we selected data from the ENTSO-E, which is the Association of European Transmission System Operator, which provides scenarios of generation and grid evolution in Europe. And in this scenario, there's up to 2/3 of renewable production in France in 2040 and 1/3 of nuclear. And regarding the European averages on the right-hand side, there's still 17% of thermal generation, of carbon-based generation, and also 2/3 of renewables in the mix. So which is a kind of difference from what we have today. So it's important to compare the impacts of these prospective scenarios compared with our current generation mix. And in this scenario, we also have other demand side flexibilities than electric vehicles, notably 12 gigawatt hours, which is a lot of stationary batteries in many countries, which are in competition with EVs for flexibility. So one of the first results I want to show you is the demand per charging port location. So on this graph, we see in blue that most of the charge is done at home in our scenario, as we selected a large number of EV chargers available at home, and also a few of them at work and at other public locations. We also see in this graph that there's much more demand on working days than on weekends, as it is found in the travel surveys. And secondly, when we compare also for uncontrolled EV charge, the charge of BEVs and hybrid electric vehicles, we see then on the left, we have some differences between how EVs are connected. So in blue are EVs that connect every day, and we see kind of a synchronous charge, synchronous demand between 18 and 21 in the evening. Whereas when EVs are connected only once in a while, or when it is needed, so when the battery is low, with the yellow and green curves, we see that the charge is much more spread through the night. And secondly, when we look at the right-hand side, for PHEVs, there's not much differences between those connection because we simulate PHEVs that maximize the share of distance they drive in electric mode. So they are kind of forced to be connected every day in order to do so. And after that, we then study and compare the 4 charging modes that are identified and that are the mostly found in the literature. So first, there's when we do not control the charge in order to have a comparison, as it is the worst case scenario. We also have the second mode, which is kind of one of the easier, which is time of use charge. So we delay the charge to the same period every day, thanks to time of use signals. And then the last 2 smart and dynamic charging modes are unidirectional smart charging and vehicle to grid, as was discussed in the first presentation. So when we look first at the smart charging diffusion, so in this graph I illustrated both emissions at the European level and the generation cost of the European system. But in the following results, I will show only the generation cost, because as we see here, these 2 parameters follow the same trends. So when we look at the left-hand side of this graph, we see that when no EVs are smartly charged, it's preferable for the system to have EVs that connect only once in a while, because as presented earlier, their charge is much more spread through the night. But when we have a lot of EVs that adopt smart charging, we illustrate how much profitable is it to have EVs that connect every day in order to maximize the charging window. Secondly, we found out also that there are two main temporal scales of flexibility. Either EVs can provide are forced to be charged every day at 100%, which is illustrated on the top of this graph, where there's some EV demand every day, and which is the most common way of studying EV flexibility today. But we also, for comparison, we also studied EVs that are allowed to be charged only once the system is ready, which means that EVs can delay their charge for 1 or 2 days, as illustrated below, especially when the system, when there is low wind and solar production, which means that the system is really carbon intensive and marginal costs are high. So yeah, as illustrated here, when we use weekly flexibility, we concentrate demand on lower generation cost days, which reduces carbon emissions and costs. So finally, when we try to compare the cost of these charging modes, we see that they are sorted in the order we expect, which is we reduce the cost for each time we add, I would say, smartness to a charge. So first we reduce the cost by around 500 million euros per year when we use time of use tariffs, and then the cost is further reduced when we use dynamic smart and when we add V2G, which reduces the cost even more to more than 1 billion euros per year at a European scale. And yeah, it is to be noted that for this study, we only compare benefits from the point of view of a charging operator. So we cannot directly convert it into cost for the end users, as we have to add the cost of the chargers and which tariff would be developed. And lastly, we also illustrate the distribution of a marginal production costs. So we see that in blue, it is when EVs are not smartly charged, and smart charging, so the red and green curves, it kinds of lowers the amount of negative and zero price time periods, but it also lowers the electricity prices at a peak demand. We also added another analysis to study how much gas prices affect these results. So we found that the reduction of cost thanks to dynamic charging goes from 1 giga-euros per year to 2.2 when we raise a lot the gas prices, which means that our results are very sensitive to other parameters in the electricity generation mix. So lastly, to conclude, I just draw a table to summarize which parameters affect the most the value of EV flexibility. So the three most important parameters we found were the gas prices and electricity generation mix to begin, and also the diffusion of smart charging and smart charging modes. And secondly and thirdly, some other parameters that are kind of impactful, but not as much as the previous one, or if we adopt daily or weekly flexibility, and whether EVs connect as much as possible or only once a week. And finally, we also have some various variants of V2G and time of use profiles. And when we look at where we are now in France in 2021, we see that we are a lot of left-hand side of this table, which means that there's still a huge potential of flexibility to be developed. And most of EVs are not smartly charged as on today. So to conclude my presentation, just 4 key results, which is first, we provided a methodology to determine various smart charging options. And we see that V2G and smart charging have, as expected, the options that decrease the most the cost. But in the end, all these options may coexist in the future of EV smart charging, depending on social acceptance. Secondly, we also found out that our optimization often force EV to be charged in the middle of the day, which kind of encourage the development of charging stations at workplace and incentivize midday connection. Thirdly, we also see kind of interest for EVs to provide weekly flexibility, which is not really ready and studied yet. So which requires further study. And finally, we are also aware that a study made only by the point of view of a national operator needs to be complemented at the local and network aspects, which requires further analysis. So thanks a lot for your attention, and I'll be happy to answer a few questions.
Thank you, Remi, for this very clear presentation, and it's fresh out of the printer or the computer. So thank you very much for this effort. There is a question. There is one question which has been raised, which regards how do you take into account the tariff design for EVs in the discussion that you introduced?
Yeah, so it's kind of I would say a gap of our study is that we only see things from the point of view of electricity generation system, which means that we provide results on the electricity production costs, but then it needs to be we do not study how to incentivize EV users to do so. So I think it's kind of the next step of this work is to study how do we distribute this marginal gain of smart charging to the EV users by creating by a tariff design that is adapted. But I think that's a whole other area of study, and I've not looked at that yet. So, but thanks for this question, because it's a great subject.
Okay, so is there other question coming from the panelists or the audience? No, no questions. Okay, then I will congratulate you once again, Remi, for this very clear presentation. And we are going to move to the Wally's presentation.
Thanks for the invitation.
Thank you.
IAEE wishes to thank. Oh wait, it's Remi. I'm sorry.
Okay, Wally, are you?
Yes. So can you hear me now?
Yep.
Okay. Thank you very much to the organizers for inviting me to give this presentation. My name is Wale Arwolo. I'm a researcher at the Sustainable Economic Group, Industrial Engineering Department at Paris Atelier University, Central Supélec. Okay, so in my presentation today, I will be talking about the framework we've developed. So I would like to start with an introduction. Okay, so why some developed countries, especially in the West, are making some progress in decarbonizing their transport sector with electric mobility. It's also important to focus attention on developing countries, since the climate change challenge is global. So how is electric mobility adoption a development issue? When is electric mobility adoption for developing countries viable, and how can developing countries transition to electric mobility? So in this presentation, I will discuss about the framework we've developed for the analysis of the integration of electric mobility and electric utilities, with a goal to guide policymakers, investors, and other stakeholders on decision-making on electric mobility investments in developing countries. So first, I'll talk about electric utilities interaction with electric mobility in the megatrends context. I'll talk about the evolution of the industrial organization of electric utilities. Then I will talk about what insights for policymakers that are willing to invest in electric mobility in developing countries, and what countries are potentially viable for electric mobility investment. So, electric utilities interaction with electric mobility in the megatrends context. So let me briefly discuss about the megatrends for those that may not be familiar with them. So these are the contemporary issues that are challenging the electricity industry. And these are decarbonization, decentralization, demand disruption, digitalization, and disintermediation. Okay, so decarbonization, so that entails the reducing carbon emissions by phasing out fossil fuels from a generation of electricity. So the use of EVs as a flexibility resource via smart charging approaches can reduce the need for investment in carbon-intensive fossil fuel-powered power plants to balance renewables generation. So on digitalization, that's the growing application of information and communication technologies in the energy system. And digitalization makes it possible to go beyond a simple time of use charging for EVs and to enhance the use of electric vehicles. Okay, digitalization can also play a role in the optimization between EV transport services and the grid services in both the planning and operation stages. Okay, digital technologies and data analytics will make it possible to also match mobility demand with power supply patterns. So about decentralization, okay, so when we'll bring more players into the market, providing supply, storage, and energy management services. EV battery storage can empower consumers to participate in the production of electricity and in demand response services, generating reverse flow along power networks and introducing the possibility of trade at the retail level. So this intermediation simply means the process of removing the middleman or intermediaries from transactions. A good example here is the blockchain technology that can facilitate the payments and billing for EV services, as well as simplify the provision of EVs flexibility services to the grid. So it can also facilitate smart charging by connecting different parties and facilitating monetary transactions between aggregators and customers through a form of open source standards, replacing proprietary solutions. So on-demand disruption, so it creates new risks and opportunities with the potential to transform the electric utilities service delivery model, reshape the stakeholders landscape, and redefine the way the government agencies and consumers engage with the energy markets. So large fractions of EV can impact the load profile of utilities by overloading the electric generation capacity, and that the introduction of EVs may require extending and reinforcing the existing electricity grid. So could have other issues like, partial total grid deflection, stranded assets risk, network cost recovery issues, etc. And as electric vehicles become a significant fraction of the fleet, would lead the whole electricity system to undergo an important paradigm change. Okay, principally the need to match generation and load becomes more challenging as the variable generation increases to represent a larger fraction of the generation mix. Okay, so I'll talk next about the evolution of the industrial organization of electric utilities. So traditionally, power systems have developed around centralized infrastructure designed to reap economics of scale and achieve simultaneous balancing of supply and demand through the one-way flow of power to passive consumers. The vertically integrated utilities have characteristics such as central planning of generation and network, cost of service remuneration of each vertically integrated utility, and they have social policy obligations. The vertically integrated utilities operate as a monopoly responsible for the generation, transmission, distribution, and retail of electricity to the end users. So that's the model one. Model two, so that's the wholesale competition. So during the 90s, we had a new paradigm for power sector reforms was put forward that emphasized the restructuring of utilities, the creation of regulators, the participation of the private sector, and the establishment of competitive power markets. Consequently, the electric utilities have faced a continuous series of changes. Technical changes to electricity generation and information technology cost declines have also allowed competition to be introduced in a lot of countries willing to reduce the cost of electricity provision. So moreover, many developed countries have liberalized the power markets to achieve performance improvements and to ensure the wholesale market yields competitive results. However, only few developing countries have introduced a wholesale power market, so reflecting the formidable list of preconditions that must be met before such markets become possible or meaningful. So the model three. Now, the combination of wholesale and retail competition. So moreover, some developed countries went a step further to establish and create competition in the retail markets. In the wholesale and retail market model, which are model 3 now, there's full access to the market for all the participants. Consumers are eligible to purchase their power supplies from competing retail suppliers. Power markets, wholesale only, and wholesale and retail, are mostly found in developed countries where the power systems are relatively large and financially stable. Across the developing world, reforms were adopted rather selectively, resulting in a hybrid model, which is model 4, the single buyer model, in which elements of market orientation coexist with continued state dominance of the sector. A key concern is that the long-term take-or-pay arrangements that are often required to induce independent power producers, investment in emerging markets can introduce distortions into power dispatch and build contractual rigidity into the power system, both of which significantly limit the scope for competition when a wholesale market is eventually introduced. So close to half of the developing countries, close to half of developing countries have adopted this hybrid buyer model, which we call model 4 here, as a sometimes indefinite step towards wholesale competition. The single buyer model often occurs after some vertical and horizontal modeling of the sector. The IPPs compete alongside the incumbent generators to supply power to the publicly owned single buyer, which is typically the transmission or sometimes the distribution utility. Although the single buyer model is often conceived as a transitional model towards a competitive market, in practice, many developing countries have remained stuck at this stage. Okay, so we'll talk about the peer-to-peer innovation with electric mobility. So with the combined impact of the megatrends transforming the electric utilities, there's a progressive peer-to-peer innovation with electric mobility unfolding in the developed and developing countries alike. This contemporary and burgeoning innovation is an unorganized local market based on peer-to-peer energy services. This innovation is under development in many countries, and it includes new decentralized storage solutions, such as electric mobility and battery energy storage systems, new communication protocols, and the coupling of local renewable energies, solar PV, wind. It also includes new market actors, such as aggregators, vehicle manufacturers, etc., and a high impact of the megatrends. Okay. So for example, there's power flow from the renewable energy sources, such as solar PV system, directly to homes and buildings, a form of decentralization. Electric mobility supported by advanced technologies and flow of communication signals, or digitalization. Renewables energy sources of generation, that's decarbonization. Bidirectional power flows from vehicles to households and buildings, which of course will lead to demand disruption and disintermediation for the utilities. So consequently, there's a gradual transformation of the electric utilities, both in the developed and the developing countries, from the model 1, 2, 3, and 4 that I discussed earlier, to include features of the peer-to-peer innovation with electric mobility. So we coined this transformation of the electric utilities industrial organization as model 1+, that's vertically integrated utilities, plus peer-to-peer innovation with electric mobility. Model 2+, that's the wholesale market, plus peer-to-peer innovation with electric mobility. Model 3+, wholesale and retail market, plus peer-to-peer innovation with electric mobility. And model 4+, which is the single buyer model, plus peer-to-peer innovation with electric mobility. So based on what I've discussed so far, so this table presents a newly developed framework to explain the transformation of the electric utilities as a result of the impact of the 5 mega trends. So many utilities in the developing countries are still in the model 1+, that is the vertically integrated utilities, plus the peer-to-peer innovation with electric mobility. So the plus sign represents the order of magnitude of the increasing impact of the mega trends on the electric utilities, depending on their industrial organization. For the developing countries, the magnitude of the transformation of the utilities with electric mobility caused by the impact of the mega trend is highest in those with functional wholesale and retail markets. That's model 3+. So you see that with 4+ signs there. It is followed by the countries with the wholesale markets. That's the model 2+. Then the single buyer model, model 4+, while it is lowest in the developing countries that are still operating state-owned, vertically integrated utilities or monopoly, represented by model 1+. So many countries in sub-Saharan Africa, for example, they appear to fall in this category, model 1+, from our research and analysis. In a situation where a developing country moves to the next model, maybe they attempt to liberalize or reform the power market, for example, from the vertically integrated utility, that's model 1+, to the single buyer hybrid model, that's model 4+. We expect the impact of the mega trend to increase as new players enter into the market. For the developed countries, the impact of the mega trends is highest in countries with wholesale and retail markets, plus peer-to-peer innovation with electric mobility. That's model 3+. So we think this framework can be useful to gain further insights on the transformation and the impact of the mega trends on the utilities with electric mobility in different developing countries. It can be further enriched with qualitative or quantitative indicators for comparative analysis among developing countries and all the developed and developing countries. Okay, so and we expect the results of this comparative analysis to be an additional tool that can provide further insights on the electric utilities and electric mobility interaction in developing countries to facilitate decision-making or policy design. So a framework can be applied to developing countries for in-depth case studies and interaction of electric mobility and electric utilities interaction. So we made a long list, finally we made a long list, so we studied all the countries to see, okay, what country belongs to what model, okay, even among all the developing countries. So we made here a long list of the developing countries that are currently model 2+ and model 3+. So these are developing countries with functional wholesale and or retail electricity market with well-functioning electric utilities. So it is noteworthy, however, that most of the developed countries where electric mobility integration with the electric utilities is currently gaining traction, they are also in this category. So in Latin America, we have Argentina, Brazil, Chile, Guatemala, Peru, and Colombia. In Eastern Europe, we have Romania, Russia, Turkey, Ukraine, and Poland. In Asia, India, China, Philippines, and Kazakhstan. And in the Caribbean, we have Dominican Republic. However, it is important to also discuss the economic challenges of electric mobility integration with utility. Of course, the most arguably most critical one is the investment cost. I mean, for developing countries that is required, maybe for the procurement of electric vehicles and or to extend and reinforce the existing grids. However, there are other challenges such as the market design and rules and the regulatory challenges and how to integrate the integration challenges with the subsystem market design. Okay, and then how do we manage the ensuing regulatory complexities and how to manage the issue of entry barrier to storage-based actors. So focusing on the investment issue. So let's give some examples. So the government of some developing countries, such as China, India, Chile, and Turkey, there are in our framework that we also identified in our framework. They are already taking the lead with investments to attract with investment, and they are also trying to attract private sector investors. So with different schemes, there are subsidies, policy support programs, and regulatory instruments, tax rebates, mandatory target for EV sales, investments in publicly accessible charging infrastructure, incentives for EV owners to install charging points, etc. So for example, China, they announced the $1.4 trillion digital infrastructure public spending program, and that includes funding for EV charging. Okay, so more than 10 cities have announced target to install about 1.2 million chargers by 2025. So in India, the FAME 2 program supports investment in EVSE for electric buses with funding up to $135 million US, to cover, and that is expected to cover the cost of one low power charger per bus and one fast charger for every 10 buses. Another example is the city of Izmir in Turkey. They've installed solar PV on the bus depot roof to provide the daily energy needed to power 20 electric buses. They installed it about 835 kilowatt, and they're planning to scale that up to 400 buses by 2025. Okay, so the government of India, again, they have the 10-year scheme to incentivize the setting up of domestic battery manufacturing through a combination of tax incentives and subsidies. And they expect that to attract about $5 billion US in total investment from global battery manufacturers. So we also see another example, China. We have about 8,000 taxis, they were electrified, supported by subsidies. And some business models are also developing. So it's noteworthy, that of Santiago in Chile. They've deployed about 776 electric buses now. And they were purchased by utility companies and leased to bus operators, so allowing the upfront cost of bus procurement to be separated from operational costs. Okay, so these are some of the investments being made by the government of some of the developing countries to encourage, to promote EV investment, to promote electromobility. And at the same time, they are hoping to use that to attract private investments into their countries. So these are some of the countries that we have identified in our framework. So to conclude, So electric utilities in developing countries, they will face more challenges with increased interaction of electric mobility in the context of the mega trends. That is decarbonization, digitalization, decentralization, demand destruction, and disintermediation. Okay. So developing countries in the Boschnim model 2+ and 3+, they appear to be good starting point for in-depth studies on the interaction of electric utilities and electric mobility, and analysis of viable investment destinations. And we made the first long list of the countries in this model 2+ and 3+, which I mentioned earlier, in Latin America, Eastern Europe, in Asia, and the Caribbean. Okay, so these are the countries we've identified so far for further or in-depth analysis. So finally, while investment costs, and that includes the need for grid extension and reinforcement, it's a critical economic challenge in the short term in developing countries. Other economic challenges, such as the integration challenges with the subsystem market design and how to manage the ensuing regulatory complexities, they also deserve attention in the short, in the mid-term, and in the long term. Okay, thank you for listening.
Thank you, Wale. There is 2 questions in the chat. One which is provocative, which is by imposing electric mobility and renewable energies on poor countries, don't you think about imposing a diet on what is starving? Which is a sort of provocative question. And the second, are there good examples for schools or university of developing countries that have used or still using electric vehicle, electric buses, like it is the case in the US now, where electric buses or school buses are starting?
Okay, so to answer your first, to answer the first question, as you said, imposing electric mobility. So it's not like a kind of imposition. Okay, it's like, okay, we're trying to do, or nations are trying to do what they consider important, to mitigate climate change. Okay, because it's a global challenge. Okay, so it's important that as it's been done in developed countries, it is also we're also trying to decarbonize in the developing countries as well. So it's not like a kind of imposition, right? Perhaps the person who asked the question is thinking maybe the developed countries are trying to kind of force the developing countries to embrace electric mobility as well. But we also all know that, pollution from air pollution from transport, from the transport sector in nations, including, of course, the developing nations, okay, kills a lot of people, thousands, or millions of people on an annual basis. So it's a global challenge, and it shouldn't be, in my opinion, it shouldn't be seen from the perspective of imposition, but rather what every nation should try to do within their, within their ability, so to speak, or their, they should consider as a priority to do on their to-do list. So that will be my answer to that. The second question, you talked about electric buses. Please, can you?
Is there some examples for schools or universities in developing countries that are used or still using electric vehicles somehow?
Yes, true. So that's why you see that I gave some examples there. There are other examples too. So like I gave the example of Chile there, and in China, of course, there's a lot. Actually, China has one of the largest deployment of electric buses globally. Okay, so that is already taking place. But again, the issue goes back to the investment cost, okay, required to make all these happen. So as nations are able to make more investment, then it will also increase the deployment of EVs or electric buses. And of course, not only to make investment or to encourage with subsidies or with financial incentives or with regulations or policy measures, but at the same time to develop sustainable business models that will encourage the private sector to also participate as well. So as the business models continue to be developed and they are viable, then we expect to see more developing countries go in this direction of the deployment of more electric buses or electric vehicles in their countries. I have answered your question.
I think so. So now we are going to move to the last presentation. So I will share my screen. There it is. Okay, so did you see it?
Yeah.
Yes. Okay, very good. So Marc-Olivier, as I told you, is stuck somewhere in Northern Europe. So I'm going to replace him in this presentation. So the idea is to present you this paper from users to operators, rationalizing charging infrastructure deployment. This is the outline of the presentation of this paper called Rationalizing Charging Infrastructure Deployment. We are going to see first the background on EVs and charging infrastructures and many issues. Then we are going to look at what are the insights from the literature. Then we are going to have an overview about the model that we are developing, and then we are going to draw some preliminary conclusions. So Marc-Olivier is the PhD student. He is finishing his PhD. I hope it will be ended in September and defended before December. So we are going to see now the background. So a bit of background. So as we all know, and it has been said already a lot. So internal combustion vehicles are polluting or source of emissions, both in terms of acoustic pollution, GHG emissions, global GHG emissions. Well, they are polluting. Electric vehicles are better on that respects, from no tailpipe emissions, a reduction of particle emissions, and reduction of noise. But there is two main barriers for EV adoption. The first is the price of the car so far. It's still much more expensive than the classical ones. And there is the range anxiety issue. And this paper is not dealing with price, it's dealing with the second barrier, which is range anxiety. And in order to solve this problem of range anxiety, you could do bigger batteries or to deploy a better charging infrastructure. What we try to do in this paper is to find a rational way to develop a better charging infrastructure. And we think that bigger batteries are not really the solution to this problem of range anxiety. At least it's not the social best solution, because it means that everyone will have to invest more on the car and use more resources. So it's better to have infrastructures and lower size of the batteries. So of course there is this organization between the charging infrastructure and the EV users and the communication standards, as we have discussed first at in this session. And there is the transportation networks, which also needs to be taken into account, in which you travel on the transportation network. The charging infrastructure must cover these transmission networks and provide energy to the EV users. Of course, if we have a charging infrastructure, we need a power grid to give electrons to the charging infrastructure. And of course, the EV user must have a home charging solution. Most of the cases, at least in Europe, people don't buy electric cars if they don't have a home charging solution. So the charging infrastructure is different in terms of cost and in terms of charging speed. The higher the speed of charging the car, the higher the cost, at least up to today's technologies. And in transportation networks, there is also different types of connecting points, highways, city streets, with different traffics and different characteristics that we need to take into account. And of course, in terms of EV users, we have different needs, different behaviors, different battery capacities, and different vehicles. So if we want to plan a charging infrastructure that makes sense, we need to take into account all these elements all together. And the research question becomes how to deploy a rational charging infrastructure that takes into account the transportation network, the charging infrastructures, and the EV user behavior. Of course, as usual, when we try to find a solution, we look at what is done in the literature before, trying to build on giants' shoulders. So what does the literature say? Oof, they say a lot of things. So we need to order a bit this charging infrastructure literature in order to put some sense in it. So what is the sense? More precisely, the literature identifies different goals, economic consideration, technical consideration, interest of different actors, and users' consideration, and with different approaches. There is basically three main ways to model the infrastructure development: flow capture of path-based type of modeling, land coverage or node-based, and event capture or tool-based, meaning that we try to understand what is the reason for people to move from point 1 to point 2 all along the day. What we want to develop as a model is a model that takes into account the user consideration and what the people are already doing on their vehicles, why they move from point A to point B and point B to point C and return to home. Of course, there's the classical chicken and egg problem. Who needs to invest first? The people buy EV in order to see the development of charging infrastructure or the development of a charging infrastructure that allows development of EVs. And who is the chicken and who is the egg? Assuming that one is the chicken and the other one is the egg, charging infrastructure must take the lead in this two-sided market development according to our research interest. So what is the type of model we are going to develop? The principle and the starting point is that the development of recharging infrastructure must support the democratization of electric vehicles. And what we need is a locational model integrating the temporal aspect of infrastructure deployment, because we didn't do an infrastructure at once or over the night. We need to build it through time. It needs to be user-centered, because if you deploy it at the right place, it's fine. But if you develop it at the worst place, it's not a deployment. And it needs to be adapted to a territory which is mixed, meaning that there is different types of roads, different people that are using it, and all these things must be taken into account. So what our model is doing, it pre-selects candidate location for charging stations. He assigns a score to each location. He places the station in order to maximize the global score of each of these locations. And he recalculates the location score with the new data it produces, and so on. He will do it until we run out of the budget that we give for the development of the charging infrastructure. So what is the score? And what do we how do we score? We try to have a set of actions that we want to optimize: the parking duration, the number of parking events, the number of distinct vehicles, the state of charge of vehicles, and the land coverage, in order to cover all the possible places with the constraints of the construction costs and, of course, the availability of the electrical grids to provide electricity. So in order to do that, what we use is we use a simulation model called MATSIM. It's a multi-agent simulation framework for transportation needs. When you see a red point, there is a problem. When it's a green point, it's not a problem. And MATSIM allows to collect data on agents' behavior. Each car is an agent. It allows to simulate the response of this agent to the addition of one station in the map, or two stations, or a group of stations on the map. And then what the model adult, and then what we put in the model is, as a constraint, is the fact that most of the vehicle never runs out of the battery. We show that the slow charging stations are more cost efficient than the high power ones, and charging stations are rather scattered than clustered, which is a result that is not seen most of the time in the discussion. So time to conclude. In terms of conclusions, EV and charging infrastructures needs to be taken into account. EV and charging infrastructure form what is called a two-sided market. We need to consider the two faces, the two sides of the market, in order to develop a rational and efficient charging infrastructure. And the first step toward a transition from combustion vehicles to electric vehicle is and needs to be done from the public infrastructure side. The charging infrastructure planning must be over time with a coherent agenda in order to have something which makes sense, and it must take into account the user behavior, which is usually the tricky part of it, and that's the reason why we use an agent-based modeling to try to understand why people are using their cars in such a way, and the impact on the charging infrastructure planning. The main result: it's possible to have EVs as convenient or even more than combustion ones, with the right development model and the right deployment model, which is a good news. The slowest and the least expensive stations are the most cost-effective in our modelization. And what is clear, if we look more in detail, is that fast charging station should be reserved for highways at the beginning and at the key point of the highways. But if we take a city, for instance, we didn't see a real cost-benefit situation to have fast charging stations more than low charging stations for a rational development of charging infrastructure grids. So thank you for your attention, and if you have questions, I will try to answer them. So I saw that there is questions. Okay, so electric cars are mostly bought by the rich, which does an average and poor consumers have to pay more taxes to pay the rich battery powered car. Okay. Yes, any innovation is normally first bought by the rich people, because usually in most situations, poor people don't buy innovations unless they can save money with it. But usually if there is a high upfront cost, we don't ask poor people to explore and suffer the cost of changing their behavior. The idea with electric vehicle is first you let the innovators try to use them to see the good and the bad of it, knowing that they have alternatives. And when the system is working, then you could by the diffusion of the technology, reduce the cost and make it accessible for most of the people. Then in terms of people paying taxes to rich people, well, normally you pay taxes according to your income. So rich people are supposed to pay more taxes than poor people. So I hope that in most countries it works like that. I'm pretty sure it's not the case, but let's say it's the classical answer to this question. Then I saw another question. So slow stations are most cost efficient. This is in cities, yes. What are the use cases for slow charging at work while shopping? In fact, in the model, we use this MatSim simulation tools, and in the MatSim simulation tool, in fact, you could put the slow charging in every place. Because you know the place. Basically, it's the map behind is the data for Berlin, and we have mapped all the Berlin zone with all the possible points for people to stop. So grocery shopping, etc., etc. In order to understand why people are moving from their place to go to work, and from going to work to back to the grocery shopping, and then to return home. So what we do with this simulation model is we take into account this daily usage of electric cars, and with the daily usage of electric cars on the public domain, taking into account that people have also a charging point at home, what we show is that mainly in urban cities, we don't need fast charging. Of course, in order to see the connection between the highways and the cities, we need to go at higher higher granularity, not take only Berlin, but to take Germany as a whole, and people moving from making 200 kilometers in order to get to Berlin and things like that, which is not easy to do so far, because we struggle a lot with the with this database and with the simulation model, because it's each round of simulations is 1 terabyte of data. So we perform all for millions of cars, millions of people, and a real infrastructure on the transportation side and on the electrical side. So to make it simple, it's not simple because we want really precise data, and we do it on a marginal increase way. So we take into account this location for slow charging first, and we probably need to go up to the region to see this effect of combination between slow charging and fast charging. Within the boundaries of the cities, it seems that it makes no sense for budget. Then if we add over criteria like confidence in the system, maybe we change the result, but with the 5 criteria we have, it seems not to be important. Then Eric, slow stations are not adapted to shopping centers which are evolving to 50 kW or more charging power. Okay, this is not what we see in Paris region. I think there is more, but depending if it's open air or if the parking is under the. Depending where the parking is located, in fact, but if it's below the shopping mall, you are not allowed to go up more than 22 kilowatt for security issues. So for 50 kilowatts, you need to be open air, and I don't think most of the the shoppings are like that. So we need to check that. The driver is about the added mileage. Okay, I didn't get read the question, but maybe it's a comment more than a question. Okay. Is there other questions, comments, or remarks? We didn't hear.
I think there is one more question here. It says 2 wheels drives, scooters, motors play a very important role in developing countries where millions of units are being sold. This will require a lot of work on adaptation of energy and mobility systems. Do you have some ideas, some comments on these issues?
Well, it was a question for the first speaker. So, but for us, we didn't take into account 2-wheelers. We just take into account cars. But I think it's not very complicated to change the agent set of control, because there are some parameters, but we didn't address that in this study. It was more cars than 2-wheelers, but it would be a good idea to add that too. But the problem is, the more we add options, the more we make turns, and the more at the end we get terabytes of data to manage. So there is a sort of rational time management issue in the modelization, in which, when you are dealing with 14 million people and stuff like this, it's quite complicated. For Berlin, we take 1% of the population, and we try once to get 10% of the population, but then we get 2 terabytes of data. So we say, okay, 1% may be enough, but when everything will work, we could do a full simulation model with all the people living around, and trying to see what is the impact of taking really everyone in the model. But let's say, with the results we have so far, we think we have already something that makes sense, and we will see afterwards if we need to go for to put more muscles in the demonstrations. But Marc-Olivier is supposed to finish his PhD in 2 or 3 months, so maybe when he will be postdoc, he will show all these muscles. We will see.
Okay, so maybe yeah, so just to chip in something, because it's I mean, the person who asked this question said it's playing a very important role in developing countries where millions of units are sold. Okay, so do you have some ideas or comments on this issue? So basically, what I will want to add here is that the planning for this also has to, happen at the local level, in this country. I know there's a lot of sales of these scooters in India, for example. There's a lot of sales, and so the planning kind of has to happen at the local level, and I think the regulator also has to be involved, and yeah, they can also try to probably learn from global best practices, right, and try to adapt it to the local situations. Find a way to adapt it to local situations, which may not be exactly the same. It may not be easily transferable. Maybe the knowledge of how to plan this type of issues may not be directly transferable, maybe from one country to the other. They can try to learn from some other countries to see how to make a kind of integrated planning model to be able to manage some of these issues, and to be able to adapt the energy and mobility system.
Okay, we are going to close the seminar on this thoughts. I would like to thank you all for your time and the efforts you put on presenting very brilliantly what you have in mind. I hope that we will organize another seminar like this next year to see the evolution of the problem through time. because each time we do that, we see that the problems evolves, and that when we solve a problem, we discover that there is a couple new just behind, which is good for researchers, but maybe it's painful for the other part of the community, but not for us, because we like solving problems. But then we will see next year what are the questions we want to answer, or we are capable to answer, and what's new on the agenda. So thank you very much, everyone, and I hope to see you all soon. Bye-bye.
Thank you.
He wishes to thank Yannick Perez and our distinguished panelists for an outstanding webinar. This webinar will be available on IAEE's website for future download. If you're not a member of IAEE, we encourage you to join by visiting www.iaee.org. We thank you for attending, and I officially close this webinar.